product between them that is another vector. And this morning we went through the geometric definition of what that is and described how you work out the vector product. Of course, gives you a vector which is perpendicular to both of the input vectors, A and B, and we described how, which of the two perpendicular directions to the plane is given by the vector product, and that's determined by the right-hand rule, which we described. It's indicated here in this little diagram. And we also described the matrix representation, or the component representation of the vector product. Okay, so that was a formula for the vector product in terms of the basis vectors I, J, and K, where the components of the vector product are just the appropriate mixture of the components of the input vectors A and B, and it is most easily remembered using this determinant formula here, where you put the basis vectors I, J, K, and the two rows. It's important to get the order right. The vector on the left in the middle row and the vector on the right in the third row. And that determinant expanded along the top row gives you the vector product. Just notice that for the most part, I'll stick with this multiplication symbol to represent the vector product, but also in use is the notation. Also in use is the notation. Okay, so some books, or some of the times, maybe some of my materials might feature this this notation, this caret symbol or up arrow symbol again, and that's the same thing as the vector product. Okay, so just don't be confused if you see that as well. Okay. Now, okay, so that was what we finished with earlier on. So we then said that we were going to list, as we introduce each new operation, we'd like to record how it relates to other operations that we have that may be in play. So there are many properties that we might put down for the cross product, but just some of the main ones are, I'll just describe those for you now. So properties of the cross product, A times B. Well, it would be nice, well, in a way you might hope it might be commutative. It's not commutative because of this right-hand rule which determines the direction. Remember, A was the forefinger, B was the middle finger, and the thumb then indicates the direction for the normal vector. But then if you swap the order of the input vectors around, that will have the effect of kind of inverting your hand and making your thumb point in the opposite direction. Okay, so the vector product A cross A, it does have the same magnitude as the vector product A cross B, but it goes in exactly the opposite direction. So you've got this negative relationship. So B cross A is the negative of A cross B. The vector that points in exactly the opposite direction. Okay. There is, however, a nice, so in a way you might call that anti-commutative. It's not commutative, but there is a nice relationship between the two orderings of the input vectors. So if you weren't here this morning, there's these notes that we handed out this morning there, at the front pile there. There is a nice distributive property. So if you want to take the vector product of A with the sum of two vectors, then the vector product operation does indeed distribute over the addition. So this is indeed A cross B plus A cross C. So we do have a distributive property. So this it distributes over addition. And indeed, it also works well with scalar multiplication. So any scalar that you have scalar or scalars that are multiplying some of these vectors, just as in the dot product, they are free to move about anywhere, okay? So the cross product of B with the scalar multiple of A, that's the same as the cross product of A with the same scalar multiple of B. And indeed, that's the same as taking the cross product with A and B first, and then doing the scalar multiple of them. Okay? So it meshes well with scalar multiplication. Now, because the vector product features the sine of the angle between the two vectors, this means that if two vectors point in the same direction, the angle between them, theta, is going to be 0, and sine of 0 is 0. Sine of 0 is 0. So that means that if you take the cross product of any vector with itself, you get the vector you get the 0 vector. Okay? So the 0 vector is a special vector. It's hard to really say what its direction is. It could have any direction whatsoever because it has 0 magnitude. Okay? So it's a special vector called the 0 vector. Okay? So the vector product of any vector with itself is the 0 vector. How does the vector product relate to our basis vectors I, j, k? Well, because of the right-hand rule, and because the vectors I, j, and k point in the directions of the x, y, and z axis, there's a nice relationship for the basis vectors I, j, and k. So for the usual I, j, and k, we have this these relationships that the vector product of I with j is the vector k. The vector product of j with k is the vector I. And lastly, the vector product of k with I will be the vector j. Okay, so that's just a quick summary of some of the properties of our vector product. But just the last couple of things to look at in this section is that so we can relate the vector product to this notion of the area of a triangle quite nicely. So if you think of two vectors A and B as, if you think of them placed end to end, if they're placed end to end, then they define a triangle. Okay? By completing the triangle with just the third side that joins the two ends of the vectors. So A and B will define a triangle. Now, what's the formula for a triangle that we normally use is that the formula for a triangle is a half times the base times the perpendicular height. Okay, so this triangle would have base. The base length of this triangle would be the magnitude of the vector b, and the perpendicular height would be the, it's a bit squash, but would be the length of that perpendicular that I've dropped from the tip of A down to B, and that is 1/2 of A 1/2 of the length of A, because A is then the hypotenuse of this left-hand side right angle triangle, times the sine of the angle theta, where theta is this angle here. Okay. So the upshot is then when we multiply, when we write down the area of the triangle like this, which is 1/2 times the base times the perpendicular height, that's this quantity 1/2 AB sine theta, where the normal way, the italic A and B there represent the respective magnitudes of the vectors A and B. Well, what you're looking at there is 1/2 times the magnitude of the vector product A times B. Okay, so there's this nice link between the vector product to another geometrical aspect of A and B. Okay? The first one was that A cross B, the vector product points in a direction perpendicular to both A and B, so it's points out of the plane, vertically out of the plane defined by A and B. But moreover, the length of A cross B is related to the length of the triangle formed by A and B. Now, the material in the next chapter, the items in the next chapter is about some basic vector geometry. So being able to talk about lines and planes in 3 dimensions using the language of vectors. But just before we do that, we just mention another aspect of vectors, which is the way they're used to describe relative quantities, relative positions, or relative velocities. So by using appropriate sums or differences of vectors, when we're using vectors, for instance, to describe relative velocities, how objects are moving relative to other objects, then you can work out combined velocities. So velocities due to the movement of one object relative to another, but then if the first object is also moving, work out the total combined velocity by using appropriate sums and differences of these velocity vectors. So there's a couple of examples here. Suppose, for instance, you have an aircraft. Now, instruments on the aircraft would be able to tell the aircraft what its wind speed is. So wind speed is the motion of the aircraft relative to the surrounding air, how fast the aircraft is experiencing its motion through the atmosphere. Okay, so that might be described by a vector v. So as far as the plane is concerned, as an object moving through the air, here's our plane. It might be moving with a certain velocity v. Presumably, it's flying straight ahead through the air. It's got a certain velocity v through the air. But of course, the air itself may be moving relative to a fixed observer on the ground. Okay, so a fixed observer on the ground may notice that there is a wind as well. So the wind might be moving. The wind might be blowing this way, for instance, with the vector w. Okay, so then the velocity of the plane relative to the fixed observer on the ground, as far as this person who's standing on the ground is concerned, the movement of the plane won't be the vector v, but the movement of the plane will be moving kind of off in this direction, which is the velocity vector v plus w. Okay. As far as the plane is concerned, relative to its environment, to just the air it's moving through, the plane is just experiencing a velocity v. But relative to a fixed observer on the ground, it would have velocity v plus w, where w was the velocity of the air, so to speak, relative to the ground. Or a second example, suppose you're on a spaceship traveling through the galaxy, and you might observe an asteroid, just a big piece of rock zooming through the galaxy. So an observer on the spaceship might measure that the asteroid is moving with a velocity vector v relative to them. Okay. So on spaceship A, they see this asteroid, and it might be moving away from them with a velocity with a velocity v. But of course, the observer A on this spaceship A flying saucer kind of spaceship, that observer on A, well, you could have another spaceship over here, and A could itself be moving relative to B. What have I said? A second spaceship B is moving with V. Oh no, so B is moving away from A, let's say, with the vector, with a velocity vector little b. So then the question is, what would the observer on B, on the spaceship B, how would they observe the asteroid? So the asteroid is moving with a velocity vector v relative to observer on this spaceship, but this spaceship over here is moving relative to this spaceship. Then that means the observer on spaceship B would observe the asteroid moving. So from B's point of view, from B's reference frame, the asteroid has velocity v minus b. Okay, so when you've got relative motion, different objects moving with respect to each other, we can often combine the effects by using appropriate sums and differences. Okay, and a little sketch diagram can often help to, figure out the appropriate thing to use. Okay. So that is going to move us on then to look at chapter 2, which starts to look at vector geometry. So the way we might use the vectors to talk about geometric objects in 3 dimensions. Or indeed, well, when talking about points and lines, it also equally well applies to 2 dimensions as well. But for the most part, we'll take 3-dimensional space as our context. As I say, the material about lines holds equally well in 2 dimensions as well. Okay, so in 3 dimensions, we have 3 basic types of geometric object. Those are points, lines, and planes. Okay, so points are the simplest things to think about. And we've already mentioned this a few times. So points are described by their position vectors. So if you have a point measured relative to some coordinate axis, we describe the position of the point using its position vector. So that's the vector that points from the origin to the point itself. Okay. Now, sometimes it's a bit of a mouthful all the time to keep saying the point with position vector r, or this point has this position vector. So sometimes, we just speed things up a bit by referring to the point r. Okay, so we abuse the language, or we abuse the terminology that way, because really r isn't, r written like this is a vector. It's not a point. But because, points are almost synonymous, or almost, for most purposes, identifiable with their position vectors, we sometimes just speed things up by saying the point r when r is a vector. And it's understood that we mean the point with position vector r. Okay? But it's still important to appreciate the difference between the 2 ideas. A point is just a kind of infinitesimal speck of a position in space. That's quite different to a vector, which is, well, in this context would be the quantity which points from the origin to the point. So it's a direction and a distance. It's a different thing to the point itself, whatever that might be. Okay, but when talking through things, we'll quite often say the point r, etc. Okay. And just another thing before we go on to lines, if you've got 2 points P1 and P2, quite often we want to refer to the vector the vector which points from one point to another one. Okay. Now, if you've got the origin down here somewhere, and if the point P1 has position vector P little p1, let's say, and the point P2 has position vector little p2, those should be straight lines. But the line from P1 to P2, this line is equal to the vector P2 minus P1. So it's the position vector of the endpoint minus the position vector of the beginning point. Okay? You can figure that out by just by using the geometric interpretation of vector addition we did earlier by sketching the triangles. So the vector between 2 points is the endpoint vector minus the starting point vector. So we'll be using that all the time. Okay. So now I want to talk about lines. How do you describe a line using vectors? Well, lines most often come to us in one of two forms. The first form is we talk about a line through a certain point, call this point P, and that the line has a certain direction which is specified by a vector D. So we talk about the line L and we say the line goes through the point P and is in the direction D. So that will define a line L through space. I'm not specifically saying whether I'm talking about 2 dimensions or 3 dimensions. It holds equally well in both cases. So we have the origin down here somewhere. The origin is down here, so there's a position vector little p for the point capital P. And then we can describe any point on the line L then in this form here. Any point on the line L will have a position vector r, which is made up of this combination. The position vector p, that will get you from the origin onto the line, onto the point P. And then you just take some multiple t times d of the direction vector d. And t times d will have the effect of moving you from the point, fixed point P, along the line. Positive values of t would send you off in the direction of d. Negative values of t would bring you back in the opposite direction to d, but still on the line L. Okay? So this is called the vector equation of the line L. If the line actually happens to pass through the origin itself, then that means it could be simplified because as your reference point P on the line, you could choose the origin itself if the line is actually going through the origin. So then this position vector P would just be the 0 vector. So in that case, you would be able to find a much simpler description of the vector equation of the line. It would just be simply r equals t times the direction vector d. So any point on the line, if it went through the origin, the position vector r of the point could be written as t times d for some value of t. However, another common way that lines arrive to us is rather than specifying a point and a direction, instead we talk about the line going through 2 points. So you've got, this time you've got 2 reference points, a P1 and a P2, and we're talking about the line that goes through them. If you supply 2 distinct points in the plane or in 3 dimensions, there'll be a unique line passing through those 2 points. So in that case, we can choose, well, we could choose one of the points, P1, as our fixed reference point. The origin will be down here somewhere. And for our direction vector, we could choose this direction vector here, which would be P2 minus P1. So that's the vector from the point P1 to the point P2. So in that case, we could write down the vector equation, the vector equation we just talked about as P1 plus T times P2 minus P1. Okay, so we're using P2 minus P1 as the direction vector D. But then we could just do a little rewriting of that. We could multiply the T into P2 and P1. So distribute the scalar multiplication over this vector difference and just rewrite it out like this. So what we're then saying is that any point on the line L will have a position vector R of the form 1 minus T times P1 plus T times P2. So any point R can be expressed as a linear combination of the 2 points P1 and P2. Now, not just any old linear combination. If you allowed any old linear combination of the two position vectors, that would describe the whole plane. It's linear combinations of a very special type. Linear combinations where the two coefficients add up to 1. Because if you add the two coefficients there, 1 minus T and T, you get the value 1. So if you just restrict the linear combinations to linear combinations like that, something times P1 plus something times P2, where the two somethings add up to 1, then you're just restricting yourself to position vectors of points along the line L. That's quite a nice way of encapsulating the line L. Moreover, if T is a small value, small positive value between 0 and 1, then the point described by R there will lie somewhere between the points P1 and P2. So a small positive value of T will be talking about the points between P1 and P2. A large positive value of T, something bigger than 1, will be points past P2. And negative values of T will correspond to points the other side of P1. So there's this nice mapping between different values, different class, different possibilities for T, and different kinds of points on the line. And more than that, when T is the special value 0, the position vector is the point P1. And then as T increases smoothly or continuously from 0 up to 1, the position vector described by R will move smoothly and continuously along the line from P1 up to P2. It will finish at P2 when T equals 1. So it just gives you this form of the equation just gives you a nice way to capture the line L, and especially if you're going to be talking about points moving along the line, it relates nice values of T to, to different types of points on the line. Okay. So that's how to talk about a line using vectors. The other type of basic geometric object in 3 dimensions would be a plane, okay? Kind of two-dimensional sheet, straight two-dimensional sheet within the 3 dimensions. And there's a couple of ways that, you might specify a plane or define a plane or single out a particular plane in 3 dimensions. One way to do that, the first way we're going to look at, is by specifying 3 distinct points on the plane. So if you pick out 3 distinct points in 3-dimensional space, there will be a unique plane, a unique straight plane in the 3 dimensions which contains those 3 points. Okay? There'll be only one plane. As long as the 3 points don't lie in a straight line. Sorry, if 3 points happen to lie in a straight line, then there'll be a whole family of planes which contain the 3 points. So I need an extra condition there. Sorry, I need a set of 3 such points will define a unique plane passing through the points. Need an extra condition there, provided the points are not collinear. If they do lie in a straight line, if they did lie in a straight line, then this plane might contain them, but also a different plane at a different angle, but still containing the line. Come out here. There'd be a whole, you could take any kind of plane at a different angle, as long as it still contained a line, it would still still would contain the 3 points which lay along that line. But as long as you got 3 distinct points which aren't in a straight line, they'll just be one single plane. And again, we can talk about, again, we form a vector equation for the plane by talking about what the position vectors are of points on that plane are like. Okay. So I'll draw a diagram for the plane here. Just to explain what's going on in this vector equation. So here's our plane represented there. The origin is off somewhere here. And we've got 3 points on the plane. P1, P2, and P3. Again, if we focus on our point P1 as being the reference point for the plane, then 2 vectors which lie in the plane will be these 2 vectors, P2 minus P1 and P3 minus P1. So those will be 2 vectors which lie parallel to the plane. And we can talk about the position vector of any point on the plane, say a point with position vector r. How do you get from the origin to r? Well, first you would go from the origin and jump onto the plane P by going up to the point P1. So you can, in order to get to r, you first go to P1, and then you would go a certain distance along P2 minus P1, and then a certain distance, and then a certain distance along the other vector, going along that vector is going along P2 minus P1, and going along this vector here would be going along P3 minus P1, okay? You jump onto the plane by going to the point P1, and then you get to the point r by going a certain distance along P2 minus P1, and then a certain distance along P3 minus P1. Okay, so the scalars a and b could be any values there, okay? And for different scalars a and b, in this equation, you get different points in the plane. And again, just as we did for lines, this equation, we can reorder it and just bring all the vectors P1 together, and that would give you this form of it here, okay, shown in the middle of the screen. And again, you see that a general point in the plane R is described as a linear combination of the points P1, P2, and P3. Not just any old linear combination, it's restricted. And the restriction is that the sum of the coefficients, the coefficient of P1, coefficient of P2, and the coefficient of P3, they have to sum to 1. Okay? Any 2 of them could be any arbitrary values, but then the third one would have to be that unique value that brought the sum of the coefficients to 1. Okay? So 1 minus A minus B, and you can have an A in front of P2 or a B in front of P3. Okay? So any linear combination of the 3 position vectors with total weight 1 will describe a point in the plane defined by P1, P2, and P3. And again, you can relate geometric aspects of the position of the point to values of the coefficients. If the points, see there in the paragraph, if the scalars a and b, if those coefficients are both between 0 and 1, that will restrict the position vector r to lie somewhere within the parallelogram defined by the 2 vectors P2 minus P1 and P3 minus P1, or somewhere within the parallelogram defined by the 3 points P1, P2, and P3. In addition, if the sum of a and b itself is between 0 and 1, then you'll be restricted to positions defined by half of the parallelogram, just by the triangle defined by the three corners P1, P2, and P3. Okay? So again, you get nice correspondence between ranges of the coefficients and geometric aspects of the plane. So that's one way to approach a plane, considering a plane is defined by 3 points. There's another way to describe it as well, and that's again to make use of a reference point on the plane, but rather than supplying 2 other reference points as well, instead implying a normal direction for the plane, or specifying what the direction is perpendicular to the plane. Okay? Because if I specify a point in space somewhere, the point at the end of my fingers here, and I also specify a direction, so I position my pen there and I use it as a vector and to point in some direction, then that defines a unique plane, because there's one and only one plane which will contain that point and be perpendicular to the vector. Okay? So choosing this reference point in front of my nose here, okay, if I just specify the point in front of my nose here, there's any old plane passing through that point, you know, there's an infinite amount of different planes. But if I specify a normal direction, that picks out one and only one plane. So if I specify the normal direction as being straight up, and the only plane that contains that point is the horizontal plane. If I change the direction to point over there somewhere, that will pick out a unique plane. Okay? So the specification of a point in a normal direction is enough to identify a plane. So what's the vector equation going to look like then? Well, moving from our previous description, we can find a normal direction to the plane by using the vector product. Okay, so you could think of the vector n as being the cross product of P2 minus P1 with P3 minus P1. Okay. But also, if you have a plane P here, you've got a reference point P1, and you've specified the normal direction to the plane. So these are all right angles between the direction vector n and the plane P. Then if you're talking about any old point R on the plane, what do I want to say here? Yeah, this special vector, which points from the reference point to the other point, this is R minus P1. Remember, the vector joining 2 points is the end point minus the initial point. That vector R minus P1 will be a vector lying in the direction parallel to the plane. Okay, so the vector n is going to be perpendicular to it. So that means it will satisfy this dot product equation here, that the dot product of n with R minus P1 will be 0. Okay, because R minus P1 will be perpendicular to n. If you just move n over here, here's n, we'll have a right angle between the two. So that would be 0. But we can rearrange that equation. Remember, the dot product distributes over vector addition or vector subtraction. So that equation is equivalent to saying n dot r is equal to n dot P1. So for any point at all on the plane, for any point r at all on the plane, when you take the dot product of n with r, you'll always get this value n dot P1. Now, P1 is just some fixed reference point in the plane. So what that final equation is saying is that when you choose any point in the plane P, the dot product of the normal vector with r will always have a fixed value. Okay? It will always have a fixed value. So the right-hand side, yeah, that's what I say there. The right-hand side does not depend on the particular point. It's just this fixed quantity n dot P1. So you could just give that a name P and say that then the plane is characterized, or the equation of the plane is then n dot r equals P. Okay. So the normal direction is specified, and the plane is then described as all the points with position vector r such that n dot r equals P. the other types of equation where you have n dot r equals some other quantity s, which is different from p, so those would be different planes, but because they have the same normal direction vector, those would be planes parallel to our first plane p. Okay? And indeed, if you smoothly or continuously vary the right-hand side of this equation for the plane p here, so n dot r equals the value p might define some plane here. As you smoothly vary the right-hand side constant p, that will describe planes that kind of smoothly move away from the original plane. So if you increase p, say, that will move the plane off in one direction, but keeping it parallel to the original plane. Or if you decrease p, that will bring the plane away from p in the other direction, away from the original plane in the other direction. Again, there's this nice connection between these parameters and the geometry of the situation as well. Okay. So that's a quick trip through some of the aspects of vector geometry, how we can use vectors to describe geometry of 2 and 3 dimensions. Your first assignment is a collection of questions based on this material. So you'll have had these before. These questions here. Now, a couple of these are about an application of the stuff we've looked at so far to the problem of closest approach, being able to judge when two lines make their closest approach to one another, or when a line makes its closest approach to a certain fixed point. Okay, so that's one of the applications that I've described here. So the problem of closest approach, finding the minimum distance between two lines, L1 and L2. Another similar problem, or another type of geometric problem we might tackle is finding the intersection, describing the points of intersection between two different planes, P1 and P2. Two different planes in 3 dimensions will always intersect in a line. So I've got an extra handout here which you can collect on your way out. Everybody takes a copy of this, and this contains the details of working out the solutions to those 2 different types of problems. Okay. But I just want to end by just showing you another quick bit of LaTeX. So now for typing up this assignment, you can choose to use Microsoft Word to produce a PDF version of your solutions, or you might try and give LaTeX a go. Now, there is a bit to, you do have to pick up some things to learn about LaTeX, but when you're within the Share LaTeX site, if you go to this help section over here, into help and documentation, there's a good set of quick, short kind of summary links there to allow you to do some of the basics of how to think about LaTeX and how to some basic help on dealing with mathematical expressions. It gives you lots of little examples of how to get different pieces of mathematics up. Okay. You'll recall in our introductory lab, I just want to show you a couple of things here. In our introductory lab, we looked at this example, this template document, LaTeX template.tech, and so I just thought I'd show you how we could just start to make some quick changes to this to, how you might just dive in and start using it. So I'll delete all of the interior material, and I'll put this file, there'll be the video recording of what we're doing now on the screen, and I'll make this file available on Moodle afterwards. Okay, so we've just got the basic bare bones there of the top matter from the template, and I've just erased everything apart from this empty begin enumerate environment there. So at the moment, my document is looking like this. It just has my first assignment, Killian, as I've replaced the author with my name, and I've got begin environments and just a one item command. So that produces this one here, my first item. And you could just start typing your solutions into here. So just as an example, I mean, one of the things we wrote down on the notes there was the list of properties of the vector dot product. So the first property, I might start typing these in. You could say the dot product is commutative. What does that mean? I.e., now, if you've been looking at this template file, the comments describe that you begin a displayed equation by doing / open square bracket. So this would be the way to type dot product of two vectors. Remember, \textbf produce the upright boldface font. The command c dot produces a centered dot. And so I want to say that this is equal to, well, the same thing. So I'll just copy and paste quickly. The same thing, but when done in the opposite order. So when you take b dot a. Put a full stop because that's the end of the sentence. And I started a displayed equation environment, so I'd have to close it off as well. So if having typed in those commands, if I compile that then, that produces the new, oh, so what have I said? Equals. Why is it saying minus? That looks like a weird, I think that might just be due to the zooming. I'll zoom in. That's some funny thing about the zooming. It appears as an equals at some zoom levels and not at others. So in the PDF, it is an equals, but it's just something funny about the zooming. But that's produced that line there. Oh, except the B isn't coming out right, because I've only just done \text. I needed textbf. Textbf. Okay, so recompile that then. Should be looking okay with both of them done in bold. So the dot product is commutative, i.e. a dot b equals b dot a. Okay. So once you get started with it, once you get into the swing of using it, it can be quite nice to write it down. This is the very last thing. If you're going to have lots of vectors in your solution, it can be a bit of a pain to be typing \textbf all the time, every time you want to just produce a single vector. So there's a neat you can write a new command. So you can make a new command to give you a shorter version of that. So you can say, I want to produce a new command. I just want to use \br to denote a vector. And that's going to stand for \textbf. So \textbf is the built-in command into LaTeX. But I'm going to, having this line will say that \br will always stand for \textbf. Okay. So I could stick in a second property. We're doing command completion there. I can put in a second item here and say the dot product plays well with scalar multiplication. I.e., and what was that property? Well, that property said if we took the scalar multiple of a vector, so this time I'm just writing \br for vectors, take the dot product of that with another vector b, but that's the same as taking the product of m with the dot product. Full stop and close the equation environment. If I recompile that, then that should have put that second property in. the dot product plays well with scalar multiplication, i.e. the dot product of M and A with B is the same as M times the dot product AB. Okay, and I've saved myself a bit of work now with this new command construction up here, because now every time I want a vector, I just have to do \vr. It's a bit quicker than typing \textbf all the time. Okay. So if you're minded to give LaTeX a go this time, or maybe with a later assignment instead of Word, have a look at some of these sample files that I'll continue to put up on Moodle, and have a look at the inbuilt help there in Share LaTeX. Lots of good tips there as well. Okay. And I'll get this file, this little file here that I've done, and put that on Moodle for you as well.